The first point is to see what the Modal-Hamiltonian interpretation says. It's a modal interpretation, and I think that everybody knows what was. It's based in an algebraic formalism, and the first postulate is a systems postulate. The quantum system is a pair, O and H, and O is the space of self-adjoint operators on a Hilbert space, and representing the observables of the system. And there is one special observable that is the Hamiltonian of the system, and we have the state that is a functional belonging to the dual space of O, and if it is the initial state of S, it evolves unitarily according to the Schrödinger or the von Neumann equation. The point is how to search or to, well, we know that if we want that certain observables have the finite value, we have to select some, just because the contextuality of quantum mechanics, we need to select a preferred context, let us say. Well, we will use this idea, the idea that where the loss does not distinguish, neither ought to distinguish. The idea is that the law, in this case, is the Schrödinger equation, and in the Schrödinger equation, the main character is the Hamiltonian. So our actualization rule, I mean, the rule that says which are, among all the observables of the system, which will take an actual value, is given by the Hamiltonian. Given the quantum system, the preferred context of definite value observable consists of H, and all the observables commuting with H and having at least its same symmetries. And we will see why later. So I will not give a justification now of this rule. The rule will be just the reason is pragmatic because it works to solve some problems. I think that many problems, interpretational problems. And it is interesting that that justification, for instance, for chemists, is not necessary because they always work on the basis of the Hamiltonian. So it's crazy because when I present this in a context of physicists or philosophers of physics, I have to explain why the Hamiltonian if all the observables are the same. And so I have to make an effort. And when I explain this in a context of chemists or philosophers of chemists, I have to explain why this is a rule and this is not obvious part of the theory. It's very interesting how different communities have different positions regarding the same. So first, I promise talk about measurement. First, I will make the difference between single measurement, like a single process, a reading of the pointer value, and the frequency measurement, a repetition of identical single measurements, in order to obtain expectation values. Yeah? Okay. In the Modal-Hamiltonian interpretation explains the definite value of the pointer both in an ideal single measurement, I mean when we have perfect correlations, and non-ideal single measurement, for instance, when we have a Stern-Gerlach with imperfect correlations, or when we have imperfect correlation, collimation of the incoming beam. I cannot develop all of this. It's published. I refer you to the papers. But it's interesting that we can explain both cases, and there was a hard criticism to modal interpretations. Harvey Brown talked about a silver bullet against modal interpretation just because the case of non-ideal measurements. I want to stress that our interpretation, even if modal, can deal with this. And in turn, in the case of non-ideal interpretation, the non-ideal measurement, single measurement, our modal interpretation distinguishes between reliable frequency measurements and not reliable frequency measurement. I mean that always, there are no ideal measurements. The measurements are always at least a little bit non-ideal. Nevertheless, physicists make measurement. So they make measurement because the frequencies they obtain and the expectation values that they compute, sometimes when the situation is well defined, sometimes it's reliable enough to get the coefficients of the state. So we have the possibility of we give a precise criterion to distinguish reliable and not reliable frequency measurements. But from the physical point of view, for us, measurement is a process that breaks symmetry. What I mean? Let us suppose a free particle. A free particle, this is the Hamiltonian. Okay, the Hamiltonian is symmetric with respect to displacements. Of course, and which one of these P will take a definite value? Of course, this is wrong here. Of course, this cannot be definite value because they don't commute to each other. But which one we will select? If we select only one of them, this is an arbitrary decision because each one is completely not indistinguishable in the sense. It's arbitrary why I decide one of the other. But if I want to measure one of them, let us suppose Pi, I have to put a wall here to measure that quantity, that observable. But in this case, the Hamiltonian is not h anymore. It's h plus a value of an observable, that represents the wall. So in this case, this potential breaks the symmetry in I. So in Y. So now we turn this observable that was not accessible because part of a symmetry, we break the symmetry and we turn it in an accessible observable by measurement. The same is in the case of the free particle with spin. Now, H is symmetric under rotation, so the component of the spin are not definite value. But if I want to make one of them, I have to use something that breaks the symmetry. What I use? Well, in this case, a magnetic field in some direction. In this case, I turn the original Hamiltonian in another Hamiltonian where this part breaks the symmetry in Z. And what I want to stress is that now, according to our definition of system, of quantum system, now the system is not the original. It's not the free particle with spin anymore. Now I have a new system where the original symmetry was broken. The same is the case of the hydrogen-like atom, any hydrogen, the hydrogen atom, for instance. We have the the quantum numbers. The quantum numbers are well defined, and these observables define a complete set of commuting observables for this system. Nevertheless, when I have a free atom, H is symmetric under rotation. Again, even if ML is a good quantum number, LZ is not defined. It cannot be a defined value observable because Z is not defined. It's any direction of the space. If I want to measure it again, I have to add a magnetic field. So now I have a new system with this Hamiltonian, and this breaks the symmetry in Z. And now it's interesting, the levels of energy of the atom began to manifest the value of ML. Previously, the value of ML was not manifest in the value of in the spectrum of the energy in this case. So what I want to say in general is that if I have the Hamiltonian, let us suppose that I have the Hamiltonian degenerate in the index G, how do you say? J. And let us suppose that I have an observable that is not degenerate. If I assume that A has a definite eigenvalue, this would distinguish among eigenvectors corresponding to a single degenerate eigenvalue of the Hamiltonian. And such a definite value would introduce an arbitrary asymmetry in the system, as we saw in the examples I showed before. So, more general, from a more general viewpoint, measurement for us is a process that breaks the symmetry of the Hamiltonian and then turns an otherwise non-definite value observable into a definite value and empirically accessible observable. So in this case, what we want to say is that measurement not only has a formal presentation like a von Neumann presentation, I mean, we accept that, but we have to see measurement from a physical viewpoint. So measurement as this process has been used successfully applied to these cases: free particle with spin, harmonic oscillation, free hydrogen atom, Zeeman effect, fine structure to the Born-Oppenheimer approximation, and optical isomerism. This is the only part is not published yet, but we hope that we will be lucky. Invariance, second point. In the paper, old paper, Brown, Suarez, and Bacigalupi said that any interpretation that selects a preferred context is committed to considering how that set is transformed under Galilean group, because the Galilean group is the group of symmetry of the theory. What we say is the preferred context should be invariant under the Galilean group. Why? Because if we think that actualization is an objective fact, something that really happens physically, it would be unacceptable that such a set changes as a mere result of a change in the perspective from which the system is described. If we accept that, then these invariant observables must be functions of the Casimir operators of the Galilean group. the Casimir operators of the Galilean group are those that are invariant under all the transformations of the group. So they have to be Casimir operators or functions of the Casimir operators. And so, which are the Casimir operators of the Galilean group? Well, this mass, square, spin, which both commute with H and do not break the symmetries. They are only multiples of identities, so they cannot break the symmetry. And this is internal energy. Of course, internal energy is not the Hamiltonian. This is true. Nevertheless, the internal energy is what carries the structure of the energy spectrum of the system. So, in fact, if we put the reference frame, we clamped the reference frame in the center of mass of the system, we have, I mean, we left aside the kinetic energy and we have only have, I mean, the Hamiltonian is the internal energy. So it is interesting that we belong from the Hamiltonian, but now, after that, we should call our interpretation Casimir modal interpretation more than Hamiltonian modal interpretation. We should change the name. So, the conclusions regarding invariance. Any realist interpretation that intends to preserve the objectivity of definite valuedness, of course, if not, must make the selection of the preferred context Galilean invariant. Therefore, it may not stand very far from the modal Hamiltonian interpretation because it has to select one or some or the Casimir operators of the group. And moreover, this can give a general framework for interpretation. The definite value observable are the Casimir operators of the corresponding symmetry group. So if we change the theory, we change the group. For instance, in quantum mechanics, we have those. But in relativistic quantum mechanics, we lose the internal energy. And this is really, take the M mass and square spin as the definite value observables is pretty reasonable because the elemental particles always have definite value of mass and spin, and these are the values that precisely define the different kinds of elemental particles. These are really relevant observables that we suppose that are always defined. And if we go, for instance, to quantum electrodynamics, we can include charge. Why? Because we can include also not only the spatio-temporal symmetry group, but also we can include the internal gauge symmetries. Finally, ontology. Well, now I will be close to what Decio said. We have some ontological references for the terms in physics and in mathematics. So we say that the observables are, in the ontology, refer to instances of universal type properties. We make the distinction between a type property, energy, and the case property, the values of the energy. And the actual case properties are not represented by the theory, but the quantum system now is not an individual because it's a bundle. It's a bundle of instances of universal properties, type properties. Probability is a propensity, and the state is a codification of the propensity on those properties. So we have no individuals at all because they are not the formalism. So we have an ontology of properties. So if the systems are not individuals, but bundles, let us suppose that we have two bundles, and each bundle is represented by the space of observables. And this is relevant because we began saying that our interpretation is based in the algebraic formalism that begins with the space of observables. So the aggregate of bundles is a new bundle where the original bundles are dissolved. Of course, if they are properties, they have no individuality because they are properties. If I put properties all together, they are still properties, and they make another bundle where the original bundles are not there anymore. So we can make a new bundle when we have a new spaces of observables where the observables are represented mathematically like this. This is well known. But the operation of bundle aggregation, when we apply it to indistinguishable particles, if we think indistinguishable bundles, if the bundles are really indistinguishable because they have no individuality, because they are not individuals, it's clearly commutative, because it's like to take a bundle of roses, and you take these roses and the other bundle, and you put the roses together, and it's the same if I take this on this, or I take this on this. The resulting bundle is the same. Depends on the order. So this is commutative. This means that we want that the final bundle, the observables of the final bundle, are represented by matrices that are symmetric with respect to the permutation of the indices that represent the original bundles. Yeah, these are the indices. I mean ¿cómo se dice? Well, these are not these are the elements of the matrices, not the matrices. So, indistinguishability now is no longer a relationship between individual particles, but it is an internal symmetry of a whole closed system that now is not an individual anymore. It's a bundle without individuality. The states of these aggregates, let us suppose that I have this aggregate with these observables. Let us suppose that I have the state. Any state, any matrix, can be written as the sum of a symmetric and an asymmetric part. Okay? This is also well known mathematically. Any matrix can be written as a sum of a symmetric matrix and an asymmetric matrix. Now, if I make an expectation value of this observable in this state, when I make the trace in this way, if this observable is symmetric, the product of an asymmetric matrix and a symmetric matrix is 0. So the expectation value is exactly the same as if the state were symmetric. But the state is not symmetric. What is symmetric is the observable, and it is symmetric for ontological reasons. So the symmetric part has no effect in its application onto symmetric observables. And this means that the symmetry of the operators representing physical states of aggregate of elemental particles with all the consideration, because there are not particles there, is not the result of an ad hoc symmetrization, but it is due to ontological reasons. That is the very structure of the ontology itself. Thank you. Ooh. Many things in short time. Sorry.
Questions? maybe a devil's advocate, or if I understand modal interpretation, it's supposed to replace some people. I believe in many words. Some people believe in Bowman mechanics. Some people believe in GRW.
Collapse.
Collapse, yes. So, if I describe a Schrödinger-Cat experiment, I understand what does it mean in many words, what does it mean in all these three. Can you give an example? I don't know if Schrödinger-Cat is too difficult, or maybe it's not. How you will describe some kind of physical situation? What is...
Well, I cannot give the explanation of all physics because I didn't do that. Nevertheless, I gave many examples of very well-known situations of physics, theoretical situations, description of a situation. For instance, isomerism. These are problems. Isomerism is a very isomers. Right hand and left hand. This is the molecules. This is a very basic problem for quantum chemists, and we can give an explanation. So, why? Because all the interpretation I know have certain problems. I'm trying to find certain problems here. I didn't find them. I suppose that because people don't read our interpretation, this is why I want to discuss. But I think that an interpretation is good as long as you can explain problems, conceptual problems in physics and chemistry, for instance.
So what is the example? You have two molecules, or what
we will explain tomorrow. Tomorrow we have a talk explicitly, yes, about isomerism. So the problem is that the Hamiltonian of the two isomers, since depending on the distances of the particles, if you want, cannot give a difference between the two isomers. But the isomers are completely different from the physical and chemical viewpoint. The properties are completely... Thalidomide, if you remember, was very, very different from...
Not about Schrödinger's cat. Isn't the answer that in the case of the cat, in spite of the superposition, you have either the cat alive or dead? That's the modal point of view. Isn't that so?
Yes, well, this is how...
You didn't know what modal interpretation says about Schrödinger's cat. So it says there is one real world, the cat is either alive or dead. But still, you have the superposition.
So if tomorrow I will be able to make interference, it will not work.
No, it will work. Yeah,
well let us discuss tomorrow with the isomerism. No, let us... well, I don't know if perhaps...
This might in some sense be a related question. A phrase that may be obvious to you but stood out to me because you used it several times was the phrase preferred context, and that may be technical jargon that I'm not familiar with. But who's doing the preference here?
No.
Who's preferring?
The preferred is the defined value context. I mean, you have all the observables of the system. You know that all together cannot take definite value because of Cauchy-Specker theorem. So, if you think that some observables have definite value, you have to decide, your interpretation, has to decide which one will take definite value. And this decision must be, coherent with physics. I cannot say anything. I can say something that then, when I apply to different physical situations, give a reasonable
maybe in my language, then I might even call that an emergent subsystem, right? Like the way you're going to chunk your system comes.
No, this is something that I will talk later with the coherence. In this case, it's an objective fact.
And can I just ask one more just quick question, just to make sure? So you gave an analogy about or you made an assumption. What was the bundle aggregation? The commutative nature of the bundle aggregation, is that an extra assumption, or was that something that's intrinsic to the interpretation, or did you have to put that extra?
The idea of the bundle.
For identical particles, there is the commutative nature of the bundle aggregation.
No, no, there is what is this is an abstract of an elemental particle is given by group considerations. Yes, it's the representation of the group. Okay, when you are talking about identical particles, so in this case, the reason is ontological. If they are identical, so I can use first one and the other. If they are not identical, not. Perhaps.
Could be a phase, but all right.
Well, I will give you the paper in which all of this was developed. I don't know. I hope that correctly.
Yes, follow-up question. Why do you single out the Hamiltonian as the special observable? It would be more reasonable to single out, for instance, position.
Well, I suppose that I was waiting for your question. Yes.
I raised my hand.
Yeah.
Link to measurement results and
Well,
immediately see by Schrödinger's cat either life or death.
Yes.
You have, as you said, you have to make a choice, and you can only make one.
You have many choices. I think that this.
But why should we
Well, because this work. I said that this is because with standard quantum mechanics, not without Bohmian, because this is another theory. This is the first thing that I didn't say, and perhaps I had to say. I'm in the context of standard quantum mechanics.
This is not the relevant point. The point is you choose one observable. You can make only one choice. And you want to make the choice in such a way that you get a link with the physics, with measurement.
Yeah. Why not changing?
Why
not changing the theory? I think that position in standard quantum mechanics will not work well. In Bohmian quantum mechanics can work well, but it is another theory. I have people of my group that will leave me to embrace and love Bohmian mechanics. It's you can have those preferences, but I'm saying that I'm taking Bohmian quantum mechanics seriously. It's another theory. It's really another theory.
Let me ask Olimpia just an internal question. I don't want to mention Bohmian mechanics. I will talk about it tomorrow. I understood that you fix the context. Now that means the Hamiltonian or the Casimir. But then everything should follow, namely experiments or measurements should not be taken as a primitive. Because somehow I had the impression in the presentation that you take experiment or measurement sort of additional primitive. No. Meaning by this that, following your presentation, you were referring to experiments. But I saw that if you fix the context, you should be able to discuss everything in terms of that observable. But if I think of a Stern-Gerlach experiment or a two-slit experiment, and you have just the energy, I have difficulty understanding how the story would go.
We really tried to explain the ontology of in general, all the interpretation without referring to measurement. This is why we talk about actualization, and this is something that does not happen with measurement, but happens. Nevertheless, I have to explain the measurement problem. This is the point. But I think that perhaps we can talk about later. We characterize measurement as an interaction that has a normal interaction, nothing primitive, a normal interaction that has to satisfy certain additional requirement to be a measurement interaction. But it is a normal interaction. Then we can give you the exactly which are. I think that you? No, Ruth.
Actually, mine's just a very short clarificatory question that goes back to the two previous. So when you say context, it's just another way of saying what Bell meant by beables, right?
Oh, perhaps, yes. Perhaps it's yes.
Pre-existing values.
Well, I just, sorry.
Existent in a certain sense. Existent value.
Yeah, so I understand your project is trying to find a physical motivation for the preferred context, and for Michael's challenge, and I understand it's usually considered that though there's this total symmetry and equivalence of all the possible observables, but that's actually broken at the relativistic level. At the relativistic level position, the space-time variables don't really work. I mean, you don't really have a position observable at the relativistic level. So that's at least one argument for why the energy basis could be more physically fundamental.
Maybe,
maybe,
but the fact is that one of the advantages of our viewpoint is that with the same context, the same, conceptual view, we can adapt this to other symmetry groups. So if we go, but really, position is never there. I'm sorry.
Well,
if we take this case, this view, you have mass, you have a spin, you have a charge, energy, but position doesn't come. It's not, it's a preference.
But I think it is objectively true that at the relativistic level, the situation is quite different from the non-relativistic level regarding certain observables.
So let us pass it to the other talk, because it's not this. ¿Lo querés poner?
Okay,